Hello and welcome to this video. In this video we're going to be looking at the topic of photons. Just a brief history first to see why we've had to come to this idea that a photon exists, and then we'll look at more about them. Originally there was always an argument between what is light. Okay, so light, we always had the argument that light is a particle or light is a wave. Okay, and originally Newton first said that light was a particle, and he did lots of calculations on it. He came up with loads of theories, but he found that what he could explain was just reflection and refraction, which could also be explained by the wave model. But what he couldn't explain was diffraction, and so we had a problem in this particle model. Whereas the wave model was first proposed by a guy called Huygens. Huygens was a Dutch physicist, obviously not as famous as Newton, so originally everyone said that light was a particle just because Newton's Newton, right? Everyone listened to Newton because he'd found out all this great stuff. He had loads of laws, and he was very highly regarded as a physicist, whereas Huygens, not so much. For most of you, this will probably be your first time hearing about Huygens. But then what happened is we had this thing called the ultraviolet catastrophe. And what that is, briefly, is that there was an experiment carried out on black body radiation. And we looked at the intensity of the radiation against the wavelength, and we found that the experimental data looks something like this. Okay, so this is what it should look like. And all of our wave models or particle models, the wave model took over from Newton's because of that idea that diffraction could be explained. So originally everyone believed Newton, but then eventually everyone turned and said that light was a wave, and that's why in key stage 3, key stage 2, you'd always be taught light is a wave. But when we found this experimental data, all of the wave ideas, the wave models, were all trying to fit this data, and all of the models that we could get, the closest thing we could get is look like this, and it would go off to have infinite energies at about this wavelength here. Okay, and we know we can't have infinite energy, so it means that at really short wavelengths we should have infinite energy. That's obviously not true. Okay, we can't have infinite energy, and we tried many different models, different theories to try and get as close to this curve as possible. We couldn't do it until a guy called Max Planck suggested that we quantize the energy. We say that instead of having a continuous source of energy, so instead of just having a wave essentially which goes and just keeps transferring energy until the wave source stops transmitting it, Max Planck suggested that we can have discrete energy packets. Okay, so discrete energy, discrete meaning that it can only take specific values. Okay, so this is why quantum physics is called quantum, because it's where we quantize everything. Okay, so it can, instead of having a continuous value like it can in the wave model, photons can only have very specific energies. And so they had discrete energy packets, and these were called photons. Okay, originally they were called quanta, but after a while we came to call them photons. So what a photon is essentially light as a particle, which is kind of a weird idea to get your head around, but we have evidence that light can behave in this way, and the evidence for this is the photoelectric effect, which is another thing that we'll go through pretty soon. So the photoelectric effect basically proves that energy has to be in discrete packets, and the photoelectric effect is actually what Einstein got his Nobel Prize for. But when we applied this idea that we have discrete energy packets, the data then that Max Planck found with his model fit exactly what the experimental data said. And this is science, so we can't argue with experimental data no matter how beautiful your theory is. Was a Richard Feynman quote. So no matter how beautiful your theory is, no matter how fundamentally great the maths looks, if it doesn't fit with experimental data, it's wrong. And so because we have these wave models that don't fit with experimental data, we said the wave model has to be wrong. But then the particle model still can't explain diffraction. So we have this idea of wave-particle duality, where light is both a wave and a particle at the same time, which is even weirder of an idea to get your head around. And this is why most people can't grasp the idea of quantum physics, because it doesn't really make sense in the real world. But what we need to know about photons is that they are discrete energy packets, and that energy is equal to hf, okay? So h is a very important number. H is Planck's constant. Okay, and Planck's constant is 6.63 times 10 to the minus 34 joules seconds. Okay, so this value you don't have to remember because it's on your formula sheet, but again, it's one of those things where you should be doing so much practice, you can just remember this off the top of your head. And F is the frequency in hertz, and E is the energy in joules, okay? So we can also, knowing that if we take a little bit of a detour here and we say that C is equal to F times lambda, which is an equation you might have met at GCSE. If not, you'll definitely meet at A-level when we come to do the waves topic. We can rearrange and say that F is equal to C over lambda, and then we can substitute this F into this equation. And so we can also have E is equal to HC over lambda. This is the second equation that you have. Now in your formula sheet, it is written as E is equal to HF is equal to HC over lambda. Don't get confused with the two equal signs. It just means the energy is equal to this, but that energy is also equal to this. So it basically means you can use either of these two to work out the energy. Okay. So now we know that light can both behave as a wave and a particle. We're going to explore this idea more when we go and look at wave-particle duality topic, but we know that photons are specifically discrete energy packets, and so when we looked in the video on energy levels, that discrete energy has to be a very specific value equal to the energy difference between the energy levels, and that's why we get that equation, referring back to the other video, that HF is equal to E2 minus E1. Okay, thank you for watching.